to our factory. Today, I will show you exactly how high-speed trains are built, step by step.
It all begins with raw materials. Massive aluminum alloy sheets, steel billets, and specialty composites arrive by the ton. Before a single cut is made, laser measurement systems scan each aluminum sheet down to 1/10 of a millimeter. Robotic arms cross-reference dimensions against digital blueprints in real time. The material storage zone alone stretches the length of several football fields. Automated carts shuttle materials between towering racks while overhead. Frame construction is where the train's skeleton takes shape. Robotic welding arms move with surgical precision, laying thousands of welds along the aluminum carbide. Every single weld is inspected using ultrasonic and X-ray scanning. Technicians trace the seams inch by inch, feeding data into real-time quality systems. Once the carbide passes inspection, it moves down the assembly line as a complete aluminum shell. At this stage, it weighs several tons, yet it's engineered to be remarkably lightweight. Meanwhile, in the forging hall, wheel production is underway. A white-hot steel billet is placed under a hydraulic press, delivering thousands of tons of force. Fresh from the forge, each wheel is heat-treated to over 900 degrees Celsius, then plunged into a quenching tank. Now comes the marriage of wheel and axle. A hydraulic press forces each wheel onto its axle with extreme precision. Laser alignment systems ensure tolerances within 1/10 of a millimeter. With the wheel set assembled, brake discs are mounted next. Each disc is machined from high-grade forged steel or carbon composite. The nose of a high-speed train is arguably its most critical aerodynamic surface. After forming, it's hand-polished to an incredibly smooth finish. Inside the bare aluminum shell, the transformation begins. Thousands of meters of cable are routed through the ceiling and walls, power lines, data networks, sensor wiring, and communication links. Window installation requires robotic suction arms that position each multi-layered glass panel with millimeter accuracy. These windows aren't ordinary glass. This is the moment engineers call the marriage, when the completed carbide is lowered onto its bogies. Each bogie is a masterpiece of engineering in itself. High-speed braking is a matter of physics and precision. Each axle-mounted brake disc measures roughly 640 millimeters across and must withstand temperatures exceeding 600 degrees during emergency stops. The brake calipers are the muscle behind the stopping power. These heavy-duty hydraulic units clamp down on the spinning discs with enormous force. Technicians install each caliper by hand. Beneath the train, a web of pneumatic lines connects the entire braking network. These high-pressure air lines feed every caliper, every actuator, and every emergency system on the train set. Before the train moves an inch, the entire braking system undergoes a full pressure test. Engineers watch as gauges climb to operating pressure. Painting a bullet train starts with aggressive surface preparation. Workers blast every square meter of aluminum with abrasive media. Robotic arms apply the primer coat in perfectly synchronized vertical sweeps. The train body rotates slowly on its stand as 4 robots work simultaneously. Now the train gets its identity. Automated spray systems glide from nose to tail, applying the main livery colors. The paint is specially formulated for rail vehicles. The final clear coat seals everything in a glossy UV-resistant shell. Then, the train rolls through a curing tunnel lined with infrared lamps. The pantograph is the train's lifeline to the power grid. Assembled on a dedicated workbench, this spring-loaded mechanism must maintain perfect contact with the overhead catenary wire. Installing the pantograph on the roof is a precision crane operation. Technicians in safety harnesses guide the 180-kilogram assembly onto its mounting plate. At the very top of the pantograph sits the carbon contact strip, the only part that physically touches the overhead wire. This strip must be perfectly flat and precisely aligned. With installation complete, the pantograph is tested through its full range of motion. Pneumatic actuators extend the scissor arms upward while engineers monitor contact pressure. Passenger comfort at 350 kilometers per hour depends on the HVAC system. Each rooftop unit is pre-assembled and tested on the ground. Overhead cranes lift each HVAC unit onto the train's roof, where harnessed workers bolt it into position. Inside the car, technicians install the ductwork that distributes conditioned air evenly to every seat. Metal ducts are clamped along the ceiling, ventilation grills positioned and sealed. Every HVAC unit connects back to the train's central management system through multi-pin harnesses. The TCMS, Train Control and Management System, is the brain of the entire train set. Technicians populate control cabinets with dozens of circuit boards, processors, and communication modules. Each control cabinet slides into a sealed compartment beneath the train floor. Cable bundles, color-coded and meticulously labeled, connect it to every subsystem on board. 28,000 cables. That's what connects a modern high-speed train from nose to tail. In accelerated time-lapse, you can see teams pulling cable bundles through management trays. With the hardware in place, the software goes in. Engineers upload millions of lines of code that govern everything from traction control algorithms to passenger display schedules. In the adjacent control room, engineers begin system-level programming. Multiple monitors display real-time data streams from every subsystem on the train. The driver's interface is programmed and calibrated next. Every touchscreen menu, every gauge, every warning indicator is tested for accuracy and response time. Now comes the moment of truth, the full systems integration test. Engineers trigger every system simultaneously. But working perfectly isn't enough. The train also has to fail safely. Engineers deliberately trigger simulated faults, a sensor dropout, a power bus failure, a communication loss. With all the hidden systems in place, the interior finishing begins. Specialized flooring panels snap together across the car floor, each one fire-rated, sound dampening, and anti-slip. Seats are bolted to precision floor rails, row by row, car by car. Each seat is engineered for ergonomics, fire safety, and easy maintenance. LED light strips come alive in sequence from back to front. Passenger information screens power on displaying route maps and destination data. The lighting system offers multiple modes. The finished cabin is a study in modern transit design. Clean lines, integrated luggage racks, adjustable lighting, and emergency equipment tucked neatly into every required position. Up front, the driver's cabin is a high-tech cockpit. Control panels illuminate with startup sequences. Pull back, and you see the full picture. An assembly hall the size of 248 football fields with multiple train sets in various stages of completion. Before the real train ever faces open air, a precision scale model enters the wind tunnel. Technicians attach dozens of pressure sensors. Wind speeds ramp up to 270 kilometers per hour. Smoke streams flow over the model's nose and body, making invisible aerodynamics visible. The data output is massive. Colorful pressure distribution maps evolve in real time across multiple screens. Drag coefficient graphs plot hundreds of data points. Crosswind stability can mean the difference between safe operation and catastrophe. The model rotates on its platform to simulate side winds at various angles. Back on the real train, static testing begins with the full electrical system. Power distribution diagrams animate across wall displays as engineers energize each circuit. Interior lights cycle through every programmed mode, full daylight brightness for stations, dimmed warmth for cruising, and emergency red for evacuation scenarios. Then comes the moment everyone waits for, the first wheel rotation. After months of assembly, the train moves under its own power for the first time. On the dedicated test track, the train accelerates from a standstill through 50, 100, 200 kilometers per hour. Engineers monitor traction performance, power consumption. At full speed, the brakes are put to the ultimate test. Deceleration graphs plot downward as the train hauls itself to a stop within precise distances. Back in the monitoring room, engineers review mountains of test data, acceleration curves, suspension deflection, power draw, vibration frequencies. Final inspection is a complete head-to-tail walk down. Engineers with tablets and scanners check every panel, every seal, every connection against a master checklist. One final stress run on the indoor test track pushes every system to its limits simultaneously. The train accelerates hard, brakes hard, and runs every subsystem at full load. Government and safety authority inspectors arrive for the official certification review. They walk the train with their own instruments, their own checklists, and their own standards. The final signature goes down on paper. An official stamp presses into the certification document. And just like that, this machine is cleared to carry passengers. The train receives its final cosmetic treatment. Workers polish every window, apply protective film to the nose, and clean every surface to showroom condition. As golden hour light floods the factory exit, the train rolls out onto open track for the first time. From above, the full scale becomes clear. The train emerges from a facility the size of a small city, gliding onto a network of tracks that will connect it to millions of passengers. But the story doesn't end at delivery. These trains are built for decades of service, and that means regular bogie overhauls, wheel reprofiling on precision lathes. Out on the main line, the train does what it was born to do. It rockets through countryside, glides into stations, boards passengers, and does it all again, hundreds of times a year. Over 500,000 individual components, more than 28,000 cables, 360 manufacturing stages, dozens of inspections, months of assembly, all for one purpose. And this is just the beginning. The next generation is already on the drawing board. Maglev systems floating on magnetic fields, hydrogen fuel cells replacing overhead wires, autonomous controls removing the need for a driver. The future of rail is accelerating as fast as the trains themselves.